right. Does anyone have any questions, comments, concerns, etc. before we get started today? All right. Let me know if you guys need anything, including and especially bathroom breaks, water breaks, or naps. If you need a nap, you are allowed to just fall asleep. I won't stop you.
You don't say.
All right, that would help if the projector was on, wouldn't it? There we go. So, last time we began chapter 4 by examining Newton's laws of motion and how they talk about force, mass, and acceleration. We're going to pick up right where we left off. Quickly glance back over these again before we start applying them to more situations. First law is the law of inertia. It states that matter is lazy, and whatever it is currently doing, it wants to keep doing until force literally forces it to change. Second law states net force equals mass times acceleration. It is a formula. It is a very useful formula. So do make sure you know it. What are words? Formula. Law number 3 is the action-reaction law. For every action force, there is an equal and opposite reaction force. And for this class, you do not have to be able to recite them verbatim from memory, but you do have to be able to know which is which and at least be able to identify them and use them in your math. What I mean by that is, say on the upcoming test, which is in about a month, I just want to keep it on your radar. What I do on the test is, rather than have you just write them from memory, I list 5 statements, and I ask you to pick out of the 5 of them which ones are the laws of motion and number them correctly. So, 2 of them are going to be distractions. Maybe they're real statements, but they won't be laws of motion. And then you have to pick out the laws of motion, which will be worded differently, but will still communicate the same meaning. So again, my goal is not for you to just memorize something. My goal is for you to be able to interpret it and understand the meaning of each one. So you do have to at least know what concepts each number refers to. So 1 is inertia, 2 is FMA, 3 is action-reaction. Sound fair so far? All right. Now, that's the wrong slide. We'll start today with just a quick sample question. I'm going to give you guys a couple of minutes to work this one through on your own or with each other before I step in and finish it with you. Here we have a 500-gram box. I'm kind of envisioning this as a four-direction tug-of-war match as seen from above. So we have an object in the middle being pulled in 4 different directions with 4 different forces. And I would like you guys to tell me the component form of the total overall force acting on this object and the total acceleration of the object. Actually, adjust that wording there slightly. Net force on the object and net acceleration of the object. So, take a couple of minutes on your own or amongst yourselves together and ponder this one, and I will see how you do. kids drawing yet? Anyone feel confident enough to tell me some numbers yet? Yeah?
50 newtons right at 25
Very good. Let's talk about how to get there. Before I do any math, just looking at the picture, what direction do you think this thing's going to start moving in? Mostly right, a little bit down. Does that sound consistent with what you guys think? All right, so I'm pointing that out ahead of time just so that we have that frame of reference to check our answer later. Here we have 4 different forces acting on this box, and I've asked you for the net force acting on this box. The definition of net force is all of the present forces added together, however many there are on any given object. Now, that said, here are some of the forces are X and here some of them are Y. So do we just want to pile all the numbers together into one straight line like that? No, we need to keep our axes distinct. So I'm going to show this using the kind of vertically oriented vector addition that we used for some of the displacement stuff the other week. And I'm going to list each vector vertically in terms of its components. Kind of starting at positive X and working counterclockwise around like geometry class tells us to. That first vector points with 250 newtons in the X and likewise none in the Y. Next, that 100 points only in the positive Y. Next we have 200 pointing left, and left is opposite right. So whatever sign you put on this first one, this needs the opposite one. Make sure that one's clear. And lastly, down is opposite up. So whatever sign you put on the 100, the 125 again needs the opposite one. And so you need to note not only axis, but also direction within that axis. And the net force should come out to 50, negative 25. Sound good so far? All right, this is again consistent with the idea that it will drift right and a little bit down. And all I asked for is the component form, so we're just going to keep the answer like this. We don't have to do any trig yet. Yeah, we're not doing trig today. Congratulations. We do want to find the net acceleration though, and we have a nice new formula for that. Net force equals mass times acceleration. And just interesting thing is that since force and A are both vectors, they have the same direction attached. So if the force points right, the acceleration also points right, because the force is what's causing the acceleration. Nice, good formula. That said, we have 2 axes here, so we're actually going to have to use it twice. Once for X, once for Y. Sigma Fx is the 50 leg. And we just plug in the mass and solve for A, right? No, what's the catch? Kilograms. How many kilograms is 500 grams? 0.5, very good. And that's going to give us an X component for our acceleration of 100 meters per second squared, because dividing by a decimal gives you a bigger answer. And we just do the same thing to the vertical component of the force. We're keeping the negative on there because it indicates down. We do need to make sure we remember that it points down. So the y component of acceleration is negative 50 meters per second squared. So if we were to write out the whole component form of our final vector, 100 comma negative 50 end parentheses meters per second squared. Main catches I wanted to point out here were, again, force is a vector, you can't add them up, but you have to track axis and direction, and remembering to convert to kilograms before you use the second law. Questions, concerns at this particular time? I'm the one that needs a nap, as it turns out. No objections? All right. Now, Newton's laws are great, and they work for any type of force you can think of. There's lots of different types of force in the universe, but they all do the same basic thing. They are all forces, they all cause mass to accelerate, and they all still add up to create net force, and as a result, net acceleration. So mathematically, forces are all used basically the same way, but it's important to note that there are different types of force, there are different sources that force can come from, and they do have their own quirks as a result of that. One interesting quirk is that there's some forces that have to be exerted via direct touch, and there's separate forces that don't, namely gravity and magnets. You don't have to be touching the Earth to be pulled by Earth's gravity. So that's one interesting quirk. Some forces are field forces that just don't require contact. But what we're going to be doing now, moving ahead this week, is beginning to look at, identify, and categorize specific types of force, talk about what sets them apart from other types of force, how we're going to use them in the class, and how they interact with other forces and Newton's laws as a whole. And the first two we're going to look at are two we've already described. I just want to make sure to get the formal definitions written in your notes for all of you. First specific force we're going to look at is gravity. You've been dealing with it your whole lives. Gravity is a force. It is specifically an attracting force between the mass of Earth and the mass of your own body. Secretly, every object in the universe creates gravity, but we'll do the math for that in like a little over a month, so don't worry about it for now. For right now, the main thing we need to use can be concerned about gravity for is figuring out the weight of specific objects on planet Earth. And the way that we do that in this class, we have a specific formula that's a variation of Newton's second law. This says that force equals mass times acceleration, and we're going to basically take that and reflavor it to be specifically about gravity. So here, this is the gravitational formula that we'll be using for most of the class. The force of gravity on planet Earth is equal to the mass of an object times lowercase g. This is the same gravitational constant that we started using a few weeks ago. Lowercase g stands for acceleration of gravity on planet Earth, and it is always negative 9.8 meters per second squared as long as you are on Earth's surface. So, we got lowercase g here. Any formula that has lowercase g in it means this. This is the constant you can plug in for it. I'll point out that the way that I've written this is not f times g, this is f with a subscript of g. So it's one thing that uses two letters within the one thing. Is that clear? Okay. So F subscript G equals mass times negative 9.8 meters per second squared. Like with this formula, you do want to use kilograms before you utilize that formula. And again, its purpose is to tell you the force of gravity that Earth exerts on anything, really, when that object is on or near Earth's surface. I'm going to point out again the difference between force of gravity and weight. Sorry, wow, that was a misnomer. Between force of gravity and mass. Weight and force of gravity are the same thing, and they are specifically the force that gravity pulls down with. As a force, it is a vector and it points down, and it depends not only on the object's mass, it depends on the gravitational strength of the planet you're standing on. Meanwhile, an object's mass is not a vector, it is a scalar that represents the amount of matter contained within the object. That does not depend on what planet you're on, so that doesn't change if you take something to the moon. Mass and weight are not the same thing as per this formula. You use one to find the other. Likewise, this number is not weight. This is the acceleration of gravity. That is the rate at which gravity pulls objects down. The force of gravity causes the acceleration of gravity, but we use the acceleration of gravity to determine what the force would need to be in order to cause that acceleration. Does that sound okay so far? Okay. So any question that takes place on planet Earth, this is automatically true. You can use this to find the weight of literally any object or organism or thing made of matter. As long as it has mass, it's going to have weight on this planet. And this number is automatically true for the acceleration of gravity as long as you do not leave Earth's surface. If something doesn't take place on Earth, that number isn't true. Even if it's in orbit, that number starts changing. And even if you go deeper into the Earth, that starts changing. Because gravity is at least partially about proximity to the object. The closer you get to Earth's core, the stronger gravity gets. So that's why all that pressure turns rock into magma. Any questions about gravity so far? Okay. The other type of force I want to examine today, I at least mentioned this one on Monday, is normal force. Do you recall when we were talking about an object sitting still on a surface, gravity is pulling it down, but something from the table is pushing up on it to keep it in place? That something is normal force. I like to write it as F subscript n, but the formula sheet calls it uppercase N. So I'm going to try to be consistent about that so that your notes match your formula sheet as close as possible. It is a force, it's just a very specifically named force, so some sources just use uppercase N. But it is a force, it acts like a force, you can use it as F in relevant places. The definition of normal force is the force a surface exerts perpendicularly out of itself to counteract a force exerted perpendicularly into itself, which is a wordy way of describing Newton's third law. Whenever something is touching a surface and exerting force into it, Newton's third law states that surface will exert a force back up and out onto the original object. I tend to think of Newton's third law using this statement. If A acts on B, then B acts on A. So if calculator presses into table, table will press out back on calculator. So the source for normal force is entirely Newton's third law. It is a reaction to the surface being pressed into. And for that reason, normal forces are extremely common. They pop up everywhere. Every object on my desk has a normal force pointing on it. You have a normal force pointing on you from both the chair and the floor beneath you. If you lean on something, normal force from the wall is holding me up right now. Pretty much any time two things are touching and one of them is not like destroying the other, there is a normal force involved. And the most common use for normal force in terms of physics math is as a counter to gravity. Usually, for something to be either sitting still or just traveling horizontally along the ground, these two concepts would have to be equal and opposite to each other for that to be the case. Because gravity's always there, and so in order to avoid falling towards Earth's core, something underneath you has to be pushing up. It's true for, and that'll be true for any organism or object that is either sitting still or moving horizontally. So very frequently, these two things will be equal and opposite. The main function of normal force, as we think about it in this class, is to oppose gravity and keep you from falling to the ground. Questions so far? Sorry. Now, I do want to mention, though, normal force and gravity are often equal and opposite, but they are not defined as being equal and opposite. There will be times where they are neither equal nor opposite. I'll talk more about that later, but if you're still writing things down now, I want to go ahead and point it out. Gravity and normal force are often opposed and equal, but they are not always opposed nor equal. They're not defined that way. What a normal force is not automatically going to be the same number as the force of gravity in a scenario. I will also point out an explanation for why we call it normal force. If it helps you to think about it this way, you can just describe it as a common, an average, a standard force, because it's everywhere. You're pretty much always going to have normal force acting on you unless you are actively falling. So it's everywhere all the time. You can think of it like that. But the reason we use the word normal is not technically for that reason, it's the math reason. Because mathematicians use the word normal as a synonym for perpendicular. I don't know why, but there's at least 3 different words for that concept: perpendicular, normal, and also orthogonal. We call it normal force because the force itself is always perpendicular to the surface creating it. All surfaces can only ever push perpendicularly out of themselves. That's even true of your own body, because when you use your hands to push on something, the force is always pointing perpendicularly out of your palm. At least most of the time. So that's the official explanation. Normal force is always perpendicular to the surface creating it. And that's why, if you're on flat horizontal ground, normal force points up and opposes gravity and keeps you from sinking. Questions so far? Excuse me, sorry. All right. That's too far. Let's just do a little bit of practice to get a sample calc or two in your notes. We're going to put a 100 kilogram box on a table. I made it kilograms this time. You're welcome. For forces, I'm usually in the habit of drawing a picture anyway. So, box, and it is currently sitting motionless on a table. Based on that little bit of information, What is the net force currently acting on this object? Say it louder. I heard someone mutter it. 0. Very good. How do we know that? It's not moving. Current velocity, 0. If its velocity stays at 0, acceleration, 0. If the acceleration is 0, then by definition, net force is 0. Does that track? Okay. Net force is 0, which means that there are forces present here, that they all just add up to 0 and cancel out. As an example of one of those forces present, what is the magnitude and direction of the force of gravity currently acting on this box? Yes, 980 newtons. In what direction does that point? Very good. Make sure you put it down. So I'm going to add that arrow to the picture. And for the sake of completeness, the way that we calculate that is using this. M times negative 9.8. I already gave you kilograms, so we don't have to convert anything. So the weight of this particular object is negative 980 newtons, the negative just meaning down. For a sense of scale, that's about what I weigh. So really, this box is about the mass of a person. Questions finding the weight? All right. Now, we know what the weight of the box is. We know what the net force acting on the box is. So, by process of elimination, what must the magnitude and direction of the normal force from the table currently acting on this box be? Very good. If the table itself is horizontal, the normal force has to point up. And the definition of net force is just the sum of all the forces that are present. There's not a more specific formula than that. You just take all the forces and add them together. And in this case, they all point in the same direction, so we don't have to worry about separating X or Y. The two forces we've identified are N up and gravity down. Whatever they are individually, they must add up to 0, and if two things add up to 0, they must be equal and opposite. So N minus 980 equals, oh, I almost wrote 980 again, 0. Therefore, N equals positive 980 newtons. So, normal force and gravity are frequently equal and opposite. Again, the normal force is what is supporting this box and keeping it from crashing through the table. Good practice. Questions, complaints? All right. With that said, let's make this a little more complicated. I mentioned that normal force and gravity are not always equal and opposite. I'm going to point out some times where they're not. So to throw a bit of a wrench into the works, we're going to take this example that we've all nicely worked out and completed, and we are going to simply place another heavy box right on top of our starting heavy box. Now, does adding that box on top of the first one change the weight of the first box? Yeah, the box, like the individual first box's weight shouldn't change, right? Because it still has the same amount of mass inside of it, and it's on the same planet. Adding that box on top didn't change Earth's pull. It is going to change the overall number of forces present on box number 1, but the weight of box 1 is unchanged. Force of gravity on box 1 would still be negative 980. Is that right? So my next question then is the normal force acting on this box going to change? Yes. I'm going to draw a second free body diagram here. We've got our 100 kilogram box. Its weight is unchanged, so I'm going to keep that negative 980 newtons down right there. But that's not the only downward pointing force present anymore, because we've added the weight of the 50 kilogram box. That's half, so I'm just going to go ahead and tell you that the 50 kilogram box would weigh 490 newtons. So that is even more downward force acting on this object. Now there still needs to be some normal force on box 1, because now box 1 is supporting 2 boxes. Normal force has to be acting on it to be holding it up so that, again, it doesn't crack the table. The scenario that we end up in is one where instead of adding 2 forces together to create our normal force, we add 3. Normal force plus the weight of box 1 plus the weight of box 2, and those all must add up to 0. They still add up to 0 because the box isn't moving. So n minus 980, also minus 490 equals 0. And as a result, by doing this, by adding box 2, we have increased normal force from 980 upwards to being 1470 upwards. Again, box 1's individualized weight doesn't change. The weight of your own body doesn't necessarily change if you are carrying something heavy. Like, your mass stays the same. You can still ditch the box if it's tiring you out. But if there's more force acting on your body, that's going to change the required amount of normal force from the surface you're standing on to keep you up. So by adding that second box, the normal force increased. And that changed our drawing from this, equal and opposite, to this, where there are 3 things that add up to 0, and none of them are the same number. Yes?
So you got, was it 490?
470? Oh, sorry, yeah. 490. That's the weight of the 50 kilograms.
Yeah, how did you get that then?
This same way we found the, did I write that down? Yeah, same way we found the weight of the first box, but it'd be 50 times negative 9.8, so it'd be half as big. I did kind of skim through that part, sorry. The point I'm trying to demonstrate here is this is a scenario where box 1's weight didn't change, but the normal force acting on it did, and we've created a scenario where that normal force is no longer equal to its weight. Same thing is true if we kind of reverse what is happening here. If instead of adding more weight onto the box, I could come along and try to lift upwards on it instead. Now, if the only force I can exert is 400, that's not going to lift the box off the table because the box weighs 980. That's not going to counteract gravity. I'm not actually going to get the box into the air. So I'd just be standing there struggling, looking like a doofus. But it does have an effect. Because if I'm applying that upward pointing 400, the table doesn't have to work as hard. I'm going to draw another picture. Again, if I'm doing this, I don't change the box's weight, but me applying that upward force means that normal force doesn't have to be as big. The normal force would only be about 580 in this case, because it would only need to be 580 to support the remaining effective weight of the box. Yeah, 580. So it is not only possible to weigh something down and increase the normal force acting on it, you can partially lift something up and reduce the normal force acting on it, because the box would not be pressing as hard into the table. Its weight stays the same, but I'm kind of alleviating some of the pressure in this case. To point out a situation where you might do this, have you ever noticed that sometimes it's easier to push something heavy along the floor if you kind of lift upwards on it slightly? Like it's moving day, moving a box or a refrigerator or something, and it's just not going to budge. But if you lift up slightly and then push it, sometimes it goes. It's a little bit easier. That's because when you do this and you reduce the overall normal force, you are alleviating the pressure from gravity. The weight's the same, but you drive the normal force down. And that we'll talk later this week about how that has an effect on friction. My point in all of this is, again, to point out normal force and gravity are often equal and opposite, but they are not by definition equal and opposite. There will be times where they're not automatically the same number. Sometimes there will be times where they don't even point in the same axis. It is possible. Actually, I can give an example of that right now. On Earth, gravity always points down. What direction is normal force from this wall pointing on me right now? Horizontally. Because normal force is always perpendicular to the surface creating it. So if I lean against a vertical wall, it would only exert normal force horizontally out of itself. So normal force and gravity are not always equal, nor are they always pointing in the opposite direction. I want to define that now up front before we start looking at weirder scenarios involving that next week. Sound fair? All right. I think that's all the points I wanted to make today. Oh, you can start packing up. I just want to point out that you may have noticed this before. When I was a kid, if I ever noticed that there was a bathroom scale in a bathroom and I would stand on it, the scale is normally next to a counter of some description. And did you also ever do that thing where you would use the counter to either lift off of the scale or press harder down onto it just to see the number change? Same thing. Because the scale doesn't actually tell you weight, it tells you normal force. The scale doesn't know about gravity, the scale doesn't calculate that, it just tells you how hard it has to press back on you. So when you press down harder into the scale by using, a counter as leverage, the number increases not because you weigh more, but because you're pressing harder into it, and it will read a bigger number because it's pressing harder back on you. Likewise, if you use the counter to lift yourself upward slightly, your weight doesn't really go down, the scale just reads a lower number because it has to exert less force to hold you up. Once again, I assume you've noticed this before. I'm just putting accurate descriptions on it. Fair deal? All right, let me know if you need anything. Have a great day. That's all. Yes, that is the emptiest one by far.